Here we go. Go live. Okay.
Okay, so I see the attendee list.
Yep, they can see you and hear you. They're all part of the webinar now.
Okay. So everyone, welcome. We'll give everybody just a few minutes, 2 minutes maybe, and we're going to get started on time because unlike the Tuesday show, we do have a time schedule that they would like us to follow. So that's something new. It's something new for this group, I know. So I see our attendees. Welcome. Cameron, Mac is here, Milton, Mr. V, Robert, and Sonali is with us today. So we'll give it a minute or two. I'm so glad everybody came out on a Friday night. For those of you for whom it is night, Cameron's probably Saturday morning for you. It's tomorrow. So we'll give everyone a minute or so. I'm getting a message here, share an image. So let's take a look here. So we'll wait just another minute or so. So I think we'll just begin. Everyone who's with us today, welcome. So glad you were able to make it out to be with us for our very first STAR class here on Slooh. My name is Keith Wasilewski. I'm going to be your host today. And the first order of business is STAR and STAR clusters. I'm sharing here a beautiful image of Sirius, which Cameron actually shared on the observation page. We're not going to talk a lot about stars today. Instead, the purpose of these classes are to be instructional how-to guides for people who are new to Slooh, teachers, students who have just started searching the heavens and are a little bit overwhelmed by the number of objects that we have to look at. And to my way of thinking, the easiest way to understand what we see with Slooh telescopes is to break it down into categories. And I figured there's no easier place, better place to start than with stars and star clusters, because that's the first thing that we see in Slooh for the most part. You know, you go outside, you look up at the sky, you see stars and probably lots of them. But there is a meaning behind what we see. So I always like to share our friend, the medieval woodcut here. You know, the ancients understood the idea of the stars and the heavens, but the more they probed and the more they explored, they realized there's a network, a mechanical clock type mechanism that governs the heavens. You know, the Greeks speak of the harmony of the spheres and this divine celestial music that is the movement of stars and planets. And we see that with the naked eye. But, you know, there's so much more that goes on. So the purpose of these classes is to kind of look beyond the veil, look behind this curtain, so to speak, and get an understanding of what these objects are that we look at. And when we talk about planets, how they move, that type of thing. So stars, like I said, these are, you know, excellent star missions on Slooh. If there's one of the things that Slooh does well, it's stars. And this beautiful picture of Cameron shows Sirius Alpha Canis Major. Beautiful diffraction pattern, diffraction spikes. Well, you know, stars are suns. They are stars, suns just like our own sun. This one in particular is much larger. I would just want to unpack a little bit. When you look at stars and you look at star names, a lot of times they'll have a common name, as this one does, Sirius, but you'll see a scientific name, Alpha Canis Major. So the Canis Major part, usually you'll see the Latin name of the constellation that the star is in. And usually in the beginning, you will see a Greek letter, Alpha, which is telling us that it's the brightest star in that constellation. So my recommendation for those starting out is become accustomed to seeing this. It's called a Bayer designation. seeing these Greek letters, which tell us how bright that star is in the particular constellation, and the constellation name that comes at the end. There's another one here that I pulled up. This was Alpha Tauri. Aldebaran is the common name. Again, it's in the constellation Taurus. It is the brightest star in Taurus. That's where the alpha part comes from. And you'll see designations with Greek letters going, alpha, beta, gamma, delta, all the way down to zeta. And then they'll start using Roman numerals and sometimes other numerals. Just get accustomed to seeing these designations. We're going to have a special series of shows just on stars because it's such a complicated process, talking about the relative brightness of stars, life cycle of stars. There are so many great Slooh quests that deal just with stars. I'm thinking of the life cycle of stars, Starlight, Starbright. So if you haven't taken some time and gone through those star quests, I recommend that you do. But we'll save stars for another time. What we're here to talk about today are star clusters. And before we take a look at some open clusters and globular clusters and talk about what they are, I want to share where they are. Now, when we see an individual star, we are looking at something that is in our Milky Way galaxy. No star that we see is out in deep space. It's just too far away. We see things that are out in deep space. Those are other types of deep sky objects. So I think to think in terms of relative distance, we have the Earth, we have our solar system, we have the moon, the sun, Mercury, Mars, Venus, Jupiter, Saturn, Uranus, Neptune. These are all objects within the solar system. When we get out of the solar system, then we start looking at things that are in the spiral arms or somewhere in the galaxy itself. And that's where we find open clusters. Open clusters are found on these spiral arms in these dust lanes in this area of stellar material that we have kind of in this belt that goes around the galaxy, the Milky Way galaxy. Our position in the galaxy is here. We're in the outer third. So we know there are about 1,100 discovered open clusters. Are there more? I mean, of course there are. There's no way of knowing what's beyond this layer of dust and dirt and interstellar material. We've really only scratched the surface. And in fact, we talk about the no-go zone, which is that north to south belt that you see in the sky. If you can see the Milky Way, astronomers really don't even look there for open clusters because there's just too much stuff up there and debris. Globular clusters, on the other hand, are in this halo that encircles the galactic core. So globular clusters are scattered out in this region. They are actually in orbit around this galactic core in a direction that's opposite that the galaxy itself is moving. So just to give you an idea of where these objects are, globular clusters are technically part of the galaxy, but they're not really in the galaxy itself like open clusters are. So with that said, we took a look at some of that. Let's stop sharing here, and we're going to take a look at our first object. And it's this one. So as we can see, open clusters are exactly like what they sound. Very loose associations of stars. Sometimes they're in a pattern, sometimes they're not. This is probably the single most famous object in the night sky after the moon or the moon and planets. It's the Pleiades. This is M45. A very, very popular open cluster here on Slooh. It's so popular, in fact, that if I had to rank the top 5 Slooh objects, I would say the moon, Jupiter, Saturn, not necessarily in that order, and probably the Pleiades and the Orion star cluster. So this is an object that is visible with the naked eye. It's one of the few open clusters that you can actually go out and see. It's been known to us since antiquity. It's a very, very often depicted and written about object. We actually have cave recordings of this at Lascaux, where the Pleiades are very, very clearly shown in the Hall of Bulls. And we may do a special party, maybe get Milton in on that one, of a combination star party with that and the visiting star of 1054. Anyway, when we look at the Pleiades, this is a different view. So when we're scheduling our Slooh missions, we have to think about a number of things. One is something that we call a field of view. So if you notice, we're only getting 3 stars here, whereas here we have 1, 2, 3, 4, 5, 6, 7. It's referred to as the 7 sisters, and then these 2. So each of these stars have names. These are the 7 sisters of antiquity in Greek mythology. After the Titans had lost their battle to take control of the heavens and the gods, Orion began to take an interest in the Pleiades, and Zeus, in very uncharacteristic behavior, decided to protect the Pleiades and turned them into doves, and they flew to the heavens to escape Orion the hunter. And in the sky, Zeus manifested himself as a bull, and when you see these in the sky, the Pleiades are protected by the bull from Orion the hunter. So we've got the 7 stars here, 1, 2, 3, 4, 5, 6, 7. These are Atlas and Pleione. These are the parents of the 7 sisters. So this is a very, very common pattern that we see. It's believed that the Pleiades formed from the same cloud of molecular material, dust, the so-called molecular cloud, and they had been moving apart from each other. That's one of the reasons that we call these open clusters. Whenever we look at objects like this in space, we have to remember that we see this 2-dimensional flat depiction, but they are in fact 3-dimensional, and they are moving. So each of these stars is gravitationally bound to each other, and they're moving through space as a group. They're also moving apart from each other. So they are moving as a group, but they're also moving apart from each other. And as they continue to move, that gravitational pull will be lost, and they'll fall into this arrangement known as a stellar association, sort of moving in their own trajectory out into space, but still maintaining to a degree this pattern that they're already in. A perfect example of this is the Big Dipper, what we know as the Plough. And the Little Dipper is another one. These are stars that are believed to have been formed from the same stellar material and have been moving apart from each other. Another example is Orion. We think that Orion was another type of these closely formed stars that have been drifting apart. So this is one of the most common objects that we see on Slooh. Beautiful to take a look at in the sky. Let me check my notes here. Is there anything else I want to say about the Pleiades? Distance-wise, these are about 440 light years away from us. These are not that far. There's another open cluster that's a little closer to us that we are going to take a look at. But that's where we are. So these are the Pleiades. Now, we are not the first people, obviously, to see the Pleiades. Like I said, they've been seen by ancient man. They've been viewed by the ancients. Go back for a minute. They're also used by the Greeks for navigation. When the Pleiades appear in the sky, it was believed that the Mediterranean was safe to travel. The Mediterranean, we think of the Mediterranean as a nice, calm body of water, but it really isn't. It can actually get quite violent. And when you read through ancient writers like Hesiod, which you can find online for free, he talks a lot about the appearance of the Pleiades and other constellations with reference to planting things, growing crops, marking the seasons by what we see in the sky. The Greeks actually have an older name for the Pleiades, the Pleiades. So it's been, in constant observation by at least the Greeks for probably close to 5,000 years, because we have an older Greek form of that word. So the Pleiades. The first person, however, to turn a telescope to the Pleiades was Galileo. First, he began looking at the moon. So when Galileo published Sidereus Nuncius, which is his groundbreaking book, he was the first person that we know of to really began to study the heavens with a telescope. And maybe not the first, this has been contested, especially recently, but he writes with great enthusiasm of looking at the Pleiades and seeing this vast number of stars, 50 or 60 stars. And again, it was one of the first images, one of the first objects that telescopes were turned to when we developed astrophotography, looking at glass plates. And I guess one of the things to think of when we turn the Slooh telescopes in our missions to the Pleiades, we want to look for a number of things. One, we're looking for nebulosity. That's that nice blue halo, that blue cloud that encircles the star itself. Now, when we look at this, it's believed that the gas cloud that we see surrounding the Pleiades is not actually the material from which the stars are formed, because the stars are moving as a group through space. The belief is that this is just a casual, casual occurrence of gas floating through space. So in this image, we see some different things going on. There's a haze around the outside. This is probably a bright object like the moon. The Pleiades and the Hyades that we're going to look at a little later form something that we call the golden gate of the ecliptic, because the moon and all the planets pass between these two objects, which give great opportunities for photos and for Slooh images and live observations. But it can be a little bit annoying when you have bright objects like the moon, and I think that's what's affecting the image here. So when we schedule our solar missions, we want to go into the object guide and have an idea of when the best times to view these objects actually are. So we have that going on here. There's also some diffraction spiking that we see here. Very similar object. Again, we see the nebulosity around some of the stars, but not all of them. When we see this pattern of 7 stars, and of course the 2 here making 9, there's usually, again, about 1,000 stars when you actually look at this through an eyepiece of a telescope or a pair of binoculars. It's a wonderful binocular object, probably one of the best. But we have our beautiful pattern here. More of the same. Again, these are Slooh images that are a little less than optimal, a little less than ideal, but I wanted to show them because it gives us an idea of what a good one is. Now, this is Astro Yavin sent me some pictures. I put out a request for some images that I wanted to use for the show. He did do some processing on this, but this gives you, again, a good idea of what you get when you choose certain telescopes for certain things. By using Canary 2 here, again, you see kind of a close-up shot. We're not seeing the entire cluster. And we have this beautiful diffraction spiking. So if you're a student and you're watching this, I want you to, for homework, try and get some images that have this type of diffraction spiking using Canary 2. You may not get something like that, but you should get something like this. That's what we're looking for. Very, very nice, very clean. And there are suggested times, optimal times for you to get these images. And that's kind of what you want to do, to have an image that comes out that looks like that. He sent me another image that shows, again, this beautiful nebulosity. This nice blue halo of gas. Again, probably not the gas that the stars were formed from, but the gas that happens to be floating out there in space as the stars move through space. The Pleiades, as I mentioned, are a naked eye object. Looks great, just going out to look for it. Looks great through binoculars. The nebulosity is something that you're not going to see with your naked eye. That's something that you need a long exposure, some type of photographic equipment like we have here on Slooh. Okay, so that's our first batch of globular open clusters. So let's look at something else. This is a globular cluster. So if we don't have that nice spread out pattern that we had with the Pleiades, open clusters. Here we have a very compact core in the center and sort of this loosely connected group of stars kind of in this nice, beautiful bundle. This is M13. This is the globular cluster in Hercules. Interesting thing about this, these are not naked eye objects. There are people that say in dark sky environments, you can see very faint smudges that may be globular clusters. I doubt that. I've never seen one. And that's simply because they're far away. Globular clusters, as I said, are in that halo area around the core of the galaxy. We're looking at 25 to 90,000 light years away, much, much, much farther. We're going to talk about some other things, but I just want to look at this image. Really, really beautiful. We've got these two stars. So one of the things to look at when you're looking at your Slooh images is don't just look at the object. Look for other things that are within it, like these guide stars around it. So some other little facts about this, as you can see, we don't have a handful of stars or a few hundred stars. You have thousands of stars. The estimate here is 300,000 stars. And the object is enormous, about 145 light years across. The other thing about globular clusters is they are extremely old. There are estimates that they're as old as the universe itself. And an interesting fact of that is the older belief is that globular clusters were single generational groupings of stars. Very, very tight, very closely knit, but from a single generation. Whereas open clusters, it's believed that these are multi-generational. And we know that for a number of reasons. You know, when you have something like the Pleiades, blue, white, very hot, very young stars, the reason we don't think that cloud of gas is related to them is because very bright stars, hot young stars like that, tend to drive off whatever gas is there. There's a lot of radiation. They have very powerful solar winds. That gas tends to dissipate. When you have something like this, how can you have something that's the age of the galaxy that only has a single generation of stars? Well, new research and a lot of new findings show us that that is not the case. Some globular clusters are believed to have 3 generations of stars. Ancient stars that are at the end of their life cycle, stars that are sort of middle age or at that point where they're no longer able to make fuel for themselves and are dying, and bright, hot, young stars. So there's a lot of changing opinions about globular clusters. And if anything we can take away from this series is that I myself don't get too wrapped up in the science, and that's because it's always changing as we continue to find out more and more and more. When we look at this image, again, we see the globular cluster, we see these stars. This is a good image. This is also a good image of the same thing, but I'm looking for something in particular, something like this. Now, this did have a little bit of processing. As we look, we're seeing greater detail, which is what happens when you process. But I'm looking at this. This is IC 4617. This is a galaxy that was captured in the same image as the globular cluster. This happens on Slooh all the time. And it makes sense. If you're looking at something that's only 440 light years away from us, like the Pleiades, not that big of a deal. This is a, we're turned to a completely different area of the universe. We're looking just outside of our galaxy. We're zoomed into this very, very different type of patch of sky. And, we're able to pick up something like this. Estimate again, 25,000 light years for the globular cluster. This galaxy, 489 million light years. It's 500 million light years away. This other image, again, of the same object, Looks a little different, just probably different atmospheric conditions. This is another little galaxy, NGC, just to show you how close together things are. We lost the star in the bottom, and by looking a little bit up top, which is what whoever scheduled this mission did, they wanted to capture this other little galaxy. And as we learned from the Hubble deep field and from the James Webb deep field images, a lot of these dots are probably galaxies too. So I'm going to pause here. Let's get out of this. Let's take a look. Are there any questions in the Q&A or the chat? All right, I guess we'll just keep going. Get my Pleiades image back up. Something I failed to mention, I forgot about. With the Pleiades, let me get my Pleiades notes. Not only are they moving through space as a group, and not only are they drifting apart, but we have to remember that the stars, like all stars, are orbiting, are rotating, on their axis. And these are huge. Blue-white stars, young stars like this, are typically very, very large. And when they orbit, when they rotate on their axis, the stars in this particular cluster are doing so at very, very high rates of speed. High rates of speed, I'm talking a day, half a day, every 12 hours. So when we think about this, it gives us an idea and some insight into this beautiful gyroscope that we have in space. Not only is it moving as a cluster, as a group, but it's moving further and further apart from each other, the stars are, and they're rotating on their axis. The rotating is so fast that it actually flattens at the poles and bulges slightly at the center, what we call an ovulated spheroid. And we see this in our own solar system. We see this with Jupiter and Saturn, who also rotate at very relatively high rates of speed. Jupiter about 9 hours, and some of these stars are doing that. So I wanted to add that in. I have that somewhere. So another open cluster. These are the Hyades. So this is roughly the same part of the sky, but not from the same cloud. And there's a number of ways that we know that. The Hyades has a mixture of young stars and older stars. So the younger stars are still in their main sequence phase, right? That's where they're still producing nuclear fusion at their cores, still converting hydrogen to helium. So they're nice and healthy. With the presence of older stars, stars that have stopped doing that and are entering into the red giant stage, tells us that this cluster is older than a cluster like the Pleiades. Now, the Pleiades will undergo this same transformation. There are some who think that is already taking place, but in the Hyades, it's definitely already started happening. And again, this is a Canary 3 image. So again, we get most of the cluster, but we can also have a narrower field of view, zooming in, cropping it, if you want to think of it that way, where we have this nice zoomed in, cropped look to the image. Here we have more stars, narrower field of view, we have fewer stars. And again, very nice diffraction patterns on the stars. That's because of the type of telescope that is used. So my homework assignment for students who are watching this, I told you a little bit about the mythology behind the Pleiades. I want you to research what is actually happening with the Hyades. They're actually related to the Pleiades. They're half sisters, but a slightly different story. Take a break here. We have a question. Here's a mosaic that Cameron made of Pleiades. Cameron, yeah, I've used a couple of your images. You have some great pictures. I want to take a look at the guides later to show everybody here that's not with us today how to go and find some of these incredible observations. It's just an endless treasure trove and resource that our members have put together, and it's something that really should get more hype. And we're going to do that today if we have time. So again, the Hyades, closer than the Pleiades, I think they're 150 light years. So relative distance, this is actually the closest open cluster to us. And again, as I said, a different age, much, much older. So again, these are just some more pictures, getting an idea of the difference of these open clusters. You can see it. Stars spread out, but in three-dimensional space with each other. Again, different distances from each other, moving through space as a group, moving apart from each other, and rotating on their axis very quickly. The interesting thing that I find when I look at these things and think about what's happening in this gyroscope and this movement is that even though they're moving at high rates of speed, if you were to somehow be able to observe them, you wouldn't really see anything. It wouldn't appear to be that way because there's nothing to compare it to. You know, it's kind of like when you're in an airplane and you don't really feel like you're moving that quickly, or you look at the ground, and it's like, yeah, you're moving, but it doesn't appear that you're going as fast as you actually are. And that's how I think it would be if we were to see these things, you know, from a spaceship or something like that. You wouldn't really have the sense of how fast they are actually moving. And of course, they're so far away from us here on Earth, we don't have any real appearance of movement unless you use scientific instruments to detect that. So let's take a look at another object. So these are my Heidi's images. I think those are done. I'm going to stop sharing. Let me go over to my other folder. So I talked a little bit about globular clusters. Again, these are not naked eye objects. In fact, the first globular cluster was not even really observed until the late 17th century by an amateur astronomer, Abraham Ile from Germany. This was, you know, when telescopes really first started coming into popular use among people who had an interest. It wasn't until really the time of Messier, and especially the Herschels. William Herschel was the first person who really got a good image of this object, M2, a globular cluster. And there are reasons for this. You know, when you think Messier was a comet hunter, he was looking for balls of fuzz that were moving. So his catalog is filled with a lot of these globular clusters, but he wasn't observing them like this. He was probably just seeing a ball of fuzz. And we know that because in order to resolve a globular cluster, you need two things. One, you need light gathering capability. You need a light bucket. You need to gather enough light to be able to, first of all, make out and see these very, very dim points. And you need magnification. And Messier, we do not believe, had either. William Herschel did. These drawings were made using probably either the 40-foot telescope, which had a 20-inch mirror. These were very late 18th, early 19th century. So my guess is he was using his big telescope by that time. He didn't just discover Uranus. He was doing a lot of work with globular clusters because he was probably the first person to really get a good look at one that wasn't a fuzz. He was able to resolve the cluster into individual stars because he had the equipment to do so. So this is what he looked at, M2. Again, we see that pattern all over again. A group of stars in gravitational relationship with each other, very tight, dense core, and the stars kind of gravitate outwards from there. So the question, I guess, could become, what do we have at the core? You know, we see the stars, what's in the middle? Well, you know, a big answer is a lot of times we don't know. The M13 images that I showed, that core is very, very dense, but the belief is that stars are close together at the rate of approximately 1 star for every cubic light year. So if you thought of a box and it was a light year in every direction, you would have a star every light year. So that's, you know, M13. Other clusters that we'll look at later have black holes. So the question becomes, what really are these things? You know, when you look at our Milky Way galaxy, you know, we have to remember that we have other objects in our neighborhood. It's what we refer to as the local group. You know, we have the Andromeda galaxy, which is about 2.5 million light years, and the Triangulum Galaxy, which is about the same distance. But we also have these other smaller galaxies. There's 80 or more objects that are similar galaxies or galaxy-like objects, and some of which is believed are these globular clusters that got pulled into the Milky Way, into these outer regions because of the gravitational effects of the galaxy. So M2, this is where we start getting into this idea of the old cliche that, you've seen one globular cluster, you've seen them all. They do all pretty much look like this, with the exception of getting different color and some different stars and features like that galaxy that I showed, that kind of thing. This is a very nice image, again, of M2. A little bit of processing. We see some of the stars brought out using some special software. M2 globular cluster that we'll come back to. And let's take a look at another open cluster. So hopefully, if you aren't familiar with how we separate these and categorize these, you're starting to get an idea. Last one or two objects we're going to look at, again, first observed by Galileo. We're talking about Praesepe, which is the open cluster that is in Cancer. Cancer is such a dim constellation that the defining object in Cancer really is this open cluster, M44, the beehive. There aren't really any bright stars in Cancer. And the way I always find Cancer is if I'm outside, you use Gemini and parts of Leo, and this pretty much lies right in between the two of them. So this is a pretty good image if it weren't for the streak, but we see it again, a combination of hot, white, young blue stars and these older stars that have started to turn, right? They're no longer in the main sequence stage. They're not creating fuel for themselves. Instead, they are reaching that red giant stage. More beehives. So this is one of my favorite objects. The ancient Greeks, again, thought of this as a type of portal. Now, this, again, is kind of a naked eye object. It does appear as a smudge in very dark sky areas, and certainly in a world that was lit only by fire, you would have a strong chance of seeing this if it were visible from where you were. But the ancients believed that this was a type of portal through which the souls from heaven passed through into mankind. Romans, the Latins, thought it looked like a manger or a crib, but I love that idea of a portal that souls pass through. This is ancient Greece. So, the ancient Greek philosophers had this concept of an understanding of there being some type of ensoulment, and this is the portal through which they passed. Again, just more pictures of this is a good one. There's obviously some processing done to this, but we get an idea of these young, hot, blue-white stars, and these stars that are approaching the end of their life. Again, we know it's an older cluster, very much like the Hyades, and in fact, it's believed that the Hyades and M44 were formed out of the same giant molecular cloud of cosmic material and interstellar gas and dust. And they think that because of the age and the proper motion or distance apart from each other. Another globular, M15. This is Pegasus, the globular cluster in Pegasus. It's not actually in Pegasus. It's kind of out on the outer reaches. It's not in the Great Square, put it that way. It's out closer to the head. Again, we see some nice stars. We talked about the core, what lies at the middle. At the center of this globular cluster, we think that there lies a black hole. So again, now we enter into that thing, black holes are at the center of what we think every galaxy. It wouldn't be every galaxy, right? Probably most. So how is there a black hole at the center of this? It's probably more galaxy-like than it is globular cluster-like. And we see that even with planets in our own solar system. Jupiter and Saturn, all the gas giants, are more star-like than they are planet-like because they're not terrestrial. They don't have a surface to land on, right? So what else do we see here? These stars, again, very, very tight, dense core, maybe a black hole at the center, gravitationally bound. Now, I've heard it said that if you were on a planet in a globular cluster, which we don't really think can happen, because if you've got a situation where you've got suns that are a light year apart, planets would probably not be able to orbit either one of them. But I have heard it said that if you were in the middle of it, it wouldn't look significantly different than if you were standing in a very, very dark place on Earth with the number of stars in the sky. But I don't really see how that can be, because our closest star is the Alpha Centauri system. Actually, I think it's Alpha Centauri B, Proxima Centauri B. And Cameron did a beautiful mosaic on that too. I've been dying to find that image. So if you have that, Cameron, please post it on Discord. Anyway, that's about 4 light years away, I think. The next closest you have, I think it's one of the HD numbers, and I think Groombridge 34 is relatively close. The next big star that's close is Sirius. That's, I think, 8 light years away. So I don't see how it could look like our night sky in the middle if you were somewhere in a globular cluster, if you were only a light year, if you had stars surrounding you that were a light year away in terms of density. I don't see how that could be. All right. Oh, I didn't want to show that. So let's go back. We'll look at 1 or 2 other things here. So hopefully, if you're at home, you're getting to see this idea of open clusters, globular clusters. Here again, I chose this one because, again, open clusters sometimes have nebulosities, sometimes they don't, and they have different relationships with these clouds that flow through space. This is the Christmas tree cluster and cone nebula. So when you're on Slooh, and you see these images and you want to go and schedule a mission to them, sometimes it will be listed under the cluster, and sometimes it will be listed under the cloud of gas, the nebulosity. And this is one of those ones that I haven't scheduled a mission to in a while. I don't remember which of the two it is. I don't remember if it's listed under the cone nebula. I don't remember, if it's listed as a nebula or as a star cluster. But again, you've got the cluster. You have a reflection nebula. The gas is actually diffracting the light from the stars within it, and it causes it to give it this beautiful purplish blue haze. Whenever you see these purplish or blue clouds on Slooh, those are reflection nebula. And the second series of shows, if we do a second series, will be on nebulosity. I wanted to start with stars, especially open clusters, because that's where we get nebulosity from. Globular clusters, we don't have nebulosity. First of all, they're so far away, I don't think we would see it if it did exist. Second of all, they're old. They're very, very old. Millions and millions of years old, billions of years old. They're almost as old as the universe itself, which is, they estimate 14 billion years. So a globular cluster is about that old. Whatever gas was floating around in there has probably been driven off and dissipated by now. The new stars that we find in these clusters probably are coming from fusions of stars where they're getting close to one another and they enter into this gravitational relationship, and then they start sharing mass, and then the process of fusion can begin all over again. I don't know if it's because they're forming out of clouds of gas as much as it is this passing of 2 stars that finally enter into that gravitational relationship with each other. This is a processed image again. Some of the things that you can do with Slooh, with the data that we have available to us, very, very clearly you can see the cluster and the nebulosity, And we even see some pinkish nebulosity. Maybe this is a type of emission nebula that's being energized by the stars behind it. So as we close up our little presentation today, we all know and love what this object is. This is the Orion Nebula, and we have this very, very bright core. Remember when I said, you know, if I had to name what I think the top 5 objects were in Slooh, this is probably in the top 5, right? The Moon, Jupiter, Saturn, Pleiades, and of course the Orion Nebula. We see tons and tons of missions scheduled to this. But what I don't see a lot of are missions scheduled to what lies at the center of the core, the object that is illuminating all of this gas, and that's the trapezium. This is an open cluster that is energizing the gas, causing it to glow like a neon lamp. And if you look at this object through a telescope at home, this is what you see. We don't see color at home. At least I don't. For that, you need processing, and Slooh uses this special method, proprietary processing, to give us these beautiful colors that we see on Slooh and long exposures. If you point a telescope at the Orion Nebula, this is what you're going to see. I love this. Everybody does. These are great images. You know, that's why we get so excited with the Slooh telescopes. But I get just as much thrill about going out and taking a telescope out and seeing this. Something so distant, so far away. And yet you can see these 4 stars, very bright, very brilliant, surrounded by this cloud of gas, like a ghost. It's just wow. So I'm going to take a little break here, getting some messages here in Q&A. So schedule your Orion missions. What am I doing? And we're going to take a look at one other globular cluster. Now, I've talked quite a bit on the Tuesday shows about John Dobson. And he had a little routine when he would do outreach or street astronomy or whatever you want to call what he did, which he did a lot of. And he said, you know, when you see a tree, it's a tree. You see a dog, it's a dog. You see a cat, it's a cat. You see a cloud, it's a cloud. You see a bird, it's a bird. When you see something like this, you don't have any words for it. We cannot process or classify something when we see something like this. This is 47 Tucanae, which is a southern hemisphere object, the gem of the southern skies. Millions and millions of stars. Just incredibly beautiful. And I wanted to share this image at the end because to me, this is just one of the most mind-blowing objects. I remember when I first saw this on Slooh and I just couldn't believe it. I used this image that was posted by Carol, and this was one of her first light objects for a telescope that she had. And it's a beautiful observation. I encourage you to go to the guides, look it up, and read what her experience with this object was. I can't even begin to imagine what it's like seeing something like this through an eyepiece. I mean, it's incredible on Slooh, but to see this live, I just cannot even imagine. And it gets better. We have Omega Centauri, another globular cluster with millions and millions of stars. I mean, wow. This is visible actually with the naked eye. It was actually thought to be a star. That's how bright it is. And it wasn't until they started to turn telescopes to it that that they realize that's what it is. Pretty incredible stuff. Another picture. So I'm going to take a little break here. Go back to my Orion image. I think that's all we had. Oh, yeah, we'll talk about these. So obvious emissions, why did I choose what I chose? There's so many other globular clusters out there. I chose a lot of images that are what I think of as if you've got to know, 3 or 4 open clusters, what do you absolutely have to see? Those are the ones that I chose. We're talking Pleiades, we're talking the Hyades, we're talking the Beehive. Those are among the most famous. There's a lot of others that I could have done, like the double cluster in Perseus. We didn't talk about this, but we have double clusters. You have a cluster of stars here, cluster of stars here, a couple of these red stars, which I don't know if these are associated with them or not, but this is just a great, great picture. Whoever took this, it's a shame that we had something fly through this with the line, but what a great image. Everything's very, very crisp, very bright. Other clusters, like Brocchi's cluster is another one I wish I could have thrown in, but I didn't. NGC 1981, which is in, Orion. We could have talked about the cluster that illumines the Running Man in Orion. There's so much we could do, but I wanted to keep it to a certain time frame. And we have other days that we can look at some of those objects and explore other parts of the sky. I just wanted to give us a taste and make it so that if you don't know how to identify these objects, now of, how to look for an open cluster, how to look at a Slooh image and say, is it an open cluster? Is it a globular cluster? We'll talk about nebulosity another day, I would imagine. We'll talk about galaxies another day. But the whole purpose of this was to demystify, for those people who are new, objects that we see on Slooh. So most people already know what the moon is. If you see Jupiter and Saturn, hopefully you know what they are. So yeah, you're off to a pretty good start already. You've got the moon, you've got 2 planets. You know what a star looks like on Slooh. We've shown you Sirius and Aldebaran. So individual stars. Now star clusters, open clusters, globular clusters. A little bit about them, so that when you schedule your Slooh missions, you have an idea of kind of what you want to do in terms of field of view. Do you want a close-up image, a kind of a cropped image, or do you want a nice big patch of the sky, depending on how big the cluster is? That was the whole purpose of what we wanted to do here. So I don't know how effective I was in that. We've got a question in the Q&A. We've got the chat. I don't know if you guys can use the chat box. So we're kind of moving into a very brief but short after party. I am going to do a couple things. One, I think we should go into Stellarium. I definitely want, for those at home who haven't ever seen these objects live, I want to close a couple things up. I am off my Zoom game. I haven't done a lot with Zoom since we got off lockdown. Try my best here. I've got a whole bunch of things open. I'm going to go install them. I'm not going to share telescopes because we don't have the 47.2 Canae mission until after 8 o'clock. So this is the night sky for me in the Northern Hemisphere. I just kind of know where this is, so I know where to look. This time of year in the wintertime, you want to look for Orion. If you've never seen Orion, you've got 3 stars in his belt. Bunch of other stars. You'll move north to Taurus. How about if I turn off the constellation lines? So what I'm using here is a program called Stellarium. A lot of us use this on Slooh. It is an absolute lifesaver when you need to find things in the night sky on Slooh. You see something on Slooh, you don't know what it is. Just go in here in the search window, type in what it is, and it'll take you right there. And you can learn all about it. So look for the 3 belt stars in Orion. You'll see a red star and an orangish reddish star. Betelgeuse in Orion, Aldebaran in Taurus. Remember, we looked at that at the beginning. And you'll see that little dipper pattern. Pleiades. This is a naked eye object. If you have binoculars, wow, this is incredible. It's probably the best binocular object in the night sky. So one of the things I always like to encourage people to do is take what you learn on Slooh and see if you can just go outside and see it. Certainly go out and look at the moon and learn about the phases of the moon. Planets certainly can trace the movement, track the movement of Mars across the night sky. We're losing Saturn, we're going to lose Jupiter, but have an idea where these things are. And when you come back to Slooh, it just adds so much, such a deeper dimension to what it is that we do on Slooh. And to me, to see those images that we looked at when we saw the Pleiades, and then to go out and take a look and be able to find it is the biggest thrill. It just gives you a type of ownership over the object that you don't have otherwise. So we have the Pleiades. Mars has just gone back into prograde motion. It was moving backwards across the background stars. It's moving in its normal direction now. Mars is very close to the Pleiades now, so you'll be able to see Mars if you've never seen Mars before. It always helps with things that you don't know, like planets. If you have a locator, so your Pleiades can be the locator for Mars once you find them. This is a great arrangement. We have that reddish orange star Aldebaran, star at the end of its life cycle. Remember, life cycle, life and death of stars quest, excellent on Slooh. I recommend that you work on that. Mars, Aldebaran. This is where the Hyades are. So once you see Aldebaran, this little open cluster are the Hyades. So we've got the Pleiades, you've got the Hyades. There is a quest for Taurus, the legend of Taurus, another great star-related quest that you can use the information that we talked about today and maybe help you complete the quest. This is what I was talking about. The Golden Gate of the ecliptic. This is something, again, that was known to the ancients. This red line, which you probably don't see very well here, is the relative path that the planets and the moon follow. It's the path certainly that the sun moves through, but we don't look at the sun usually, unless you're using a solar telescope. But everything passes through here. So once a month, you're going to see the moon pass through here. You're going to see Jupiter pass through. You'll see Saturn pass through. Mars also follows this path. So we have some incredible opportunities, not just for viewing, but also for using the Slooh telescopes to see if you can fit this into the field of view. Sometimes we can, sometimes we can't. You can use a little bit of Slooh magic or some processing magic and stitch things together and fit things in if they don't fit into the telescope. But it's just a great opportunity. And there are all kinds of articles online that alert us to when this is happening in case you don't watch it yourself. So we have those. And we talked about the what are we talking about? The beehive M44. So here's my finder for M44. You're going to look for the 2 bright stars in Gemini. So you've got that. You've got Sirius, Gemini, and you're going to look for Leo. Leo is the backwards question mark, and you will look for the star Regulus, which is the bright star there, Castor, Pollux, and you just have to kind of look in the middle if you've got binoculars, this is a binocular object, you're not going to see anything. Halfway between the two of them, more or less, you have Precipe, that beautiful portal through which souls pass from the heavens to people here on earth, according to the ancient Greeks, or the crib that the Romans saw. It's a beautiful binocular object. After the Pleiades, which is fantastic, this is the second best object. The cool thing is, even if you don't have binoculars, start learning your way around the night sky if you don't know it already. Look for the backwards question mark. Look for Regulus. Look for Castor and Pollux and Gemini. And just point to the middle of the the middle of the sky. Tell someone at home, right there, that picture that I took on Slooh, that's where it is. Go up here into Taurus and say, right there, those pictures that we took on Slooh. Those are the Pleiades. It's an exciting thing to do, a lot of fun. So I was having some requests here for some Slooh images. I can't just put up a picture because I closed all that stuff. Let me get on Slooh. All right. Let me take a look here. What am I sharing? I don't even know where I'm at.
Fantastic comment here from Cameron, who says, here in New Zealand, we call the Pleiades the Matariki, and we have a national holiday to celebrate its heliacal, I probably did pronounce that correct, rising. And Orion's belt is the perch of a wood pigeon, with Betelgeuse being the ripe red berry the pigeon is attempting to eat. Oh, thanks for sharing that, Cameron.
Yeah, different cultures, of course, see the same things that we see, and there are so many stories. Well, let me pull, I want to get into, I don't know why this let me do this. I want to get into Slooh here, and we will take a look at how to find some of these other stories that we see without having to do a whole lot of research. So these are some live Slooh images. I know that I had some stuff scheduled. Oh, we're going to get the Canaries. I'm sorry, Chile. So let's take a look. I hadn't planned on doing this. We didn't plan on some of these other. Oh, why am I getting my voice? Stories that we see without having to do a whole lot of research. So these are some. I'm not really sure what happened there. Anyway, let's take a look at Chile. I had requests for this, but we already looked at the objects. I'm not really sure what happened there. Anyway, let's take a look at Chile. I had requests for this, but we already looked at the objects. I don't know why it's doing this. Gretchen, what's happening here?
Okay, I think you have the event page open in your browser.
Not really sure what happened there. I don't think I do. I've got so many screens open. I don't know what's going on.
Yeah, so just go ahead and close all of those, and you want to open up Slooh just to the telescopes. I'd close everything on Slooh down, and then just bring it back up. Go back to this.
Close. I've got everything close.
Okay.
Well, we looked at the Slooh objects anyway. It's 47 to connect. So that's where we find these objects in the stellarium. I just want to show everybody at home who's not here with us today how to use this new revamped object page because I hadn't used this in quite some time. And it's just fantastic. So the way that you do this, people at home, students who are using this for the first couple times, teachers who are new that need to teach this to students, you just go to the search bar, Pleiades, what? Of course, okay, made a mistake. So you just go to the Pleiades in the little magnifying glass. You've got all of this great information. You get an overview, you get a popular image. You can go to observations. This is where I got some of my great pictures from. Karen's got one in here, and some other people. Some are processed, some aren't. And I like that because it gives you an idea of what you can do with the Slooh telescope. Sometimes you get great images right from the telescope raw, and a lot of people don't process anything. They don't do anything. And then we have people that get very involved with astrophotography and stack images and play around with that way. But there, it's a good place to go and see observations on specific images, specific types of objects or things that you're looking for. Now, not every object has a guide. I really wanted to put Rocky's cluster in here, but it does not have a guide. Missions are the other thing. And one of the things I'm going to start doing, if we get schools on board with this, is I will start scheduling missions at the optimal times so that when you see my name pop up in a mission, you know that we're picking a time where you're going to get the best possible image. So you do have this graph. We want to get our objects when they're as close to the top as possible. So Pleiades, around 2050, right? Why does it get lower here? It's because it's setting. So you want to get the object when it's nice and high in the sky. And you can see the suggestion missions are all around that time, 1940, 2030, 2020, 2050. They also have one for the observatories in Chile. It's already in the downhill here because by the time they open, the object is already getting ready to set. It's already past what we call the meridian, the imaginary line in the sky, and it's no longer rising, it's setting. It's typical for this time of year. You can look for another object. The Hyades has an object page too. So this was homework for everybody. So here's my Hyades. Something that always interested me. Charles Messier was looking for balls of fuzz in the sky. He had no problem choosing the Pleiades for an object, but he didn't pick the Hyades. He definitely padded his list. Nobody would mistake the Pleiades for a comet or some of the other objects that he added. Globular clusters, of course, I can see that, right? Because they're just balls of fuzz in the sky. But he didn't include the Hyades. We also have, if you got a burning question about an object, you can go to AAA, Ask an Astronomer. Eliminations, this doesn't have any related source, but usually you may have a poem or a story or an artwork or a type of observation that isn't scientific or doesn't share anything about the object so much. Maybe it's a personal reflection that will wind up in illuminations. Those are always very interesting. Again, the missions and the overview. In the overview, there's another great section on the bottom called Burnham's Corner. I'm going to click on Burnham's Corner. This is a tribute to the great author, Robert Burnham, who wrote a 3-volume series of books called Burnham's Celestial Handbook. They are a must-read if you can find a set. They've been out of print for some time. I have 2 sets. I like them so much. But you don't need to buy a set because the relevant information, a lot of it, is right here on Slooh. So you can enjoy a large part of Burnham's writings on these objects, which includes a lot of mythology, some science. Just, it's a great, I consider to be one of the greatest series of books about anything ever written. Robert Burnham actually hand-typed the manuscript for this. Was originally I think in loose leaf form. It came in a binder, and it was eventually published by Dover. And as I said, it has been out of print. I like this section on Slooh because the handbook has a lot of data that we don't really need to know, unless you're really into some of the more scientific aspects of what we look at with the Slooh telescopes. He also uses a different type of coordinate system, which doesn't always lend itself well to the Slooh telescopes. Lend itself well means it might not be centered. But anyway, that's something to check out. So we took you to Burnham's Celestial Handbook. And it's 10 after. We're just about done. I don't know, Gretchen, do you think we have time to do a fly through?
Sure, if you want to.
Yeah, I want to. While I'm waiting for this program to load, I just wanted to thank everybody for coming today, putting up with my inconsistencies. Sometimes this is my first time doing this solo. Usually we have an interactive group, and unfortunately didn't have that today. But I'm going to take the time to share one last thing with you. And we're going to go into a program that I use a lot. It's called Celestia. This is my special treat. Anytime that I'm with a group, I always like to leave them with something. So here I'm going to use this. Celestia has a little go to object thing. I loaded this object because not everything is loaded in Celestia. Okay, I did something wrong. All right, now I have to back up a little bit. So if you remember our little fly through, the Pleiades, every object that we see is at a different distance from us. The ancients didn't think that. They thought everything was the same distance, and it's still a beautiful visual to use when we think of the celestial sphere, when we think of the Earth being surrounded by this globe, because we are in a lot of ways. It's a good way to think about it, but it's not flat. Things are not at the same distance. It's just that globe continues. We can go in infinite distance in any direction. So when we think of these objects like the Pleiades, that's what we have to keep in mind. As I zoom in, you can see clearly that there is a distance between them as I fly through and as I fly back. You don't see the nebulosity here, so we're not seeing the cloud. But we are seeing, because of where we are, the pattern. And this gives us the other idea that the only reason we see that little dipper pattern is because of where we are on Earth. If we were to view this from a different vantage point, the pattern vanishes. It takes on a completely different pattern. Now, you'd have to be way out in space to see a difference because, again, they're very far away. 450 light years is not close. So if we do that and we fly through, it's a different experience. And the distances between these are vast. A light year is very far. It's not far in space terms, but in terms of actual distance, yeah, it is. So that's my Celestia fly through. And I think with that, unless there are any questions, I think we're going to call it a night. So again, I want to thank everybody for joining us today. If you have anything that you want to add, you can add it in Q&A. I don't know if you have access to the chat room or the chat box. I'm going to give a plug for our show on Tuesdays. Tuesdays at 8 o'clock. That's Eastern Standard Time. UTC, I think that's right at I don't know what time it is, UTC. We're UTC -5. So I guess that's 1 o'clock in the morning. I think they listed as 12:59 UTC. No, 59 UTC. I don't look on the Slooh page and you can find, we have that show on Discord. A little different than this. It was interactive. We take lots of questions, lots of chatter back and forth. We have a good time. But I wanted to, yeah, we can. So we're talking about having an after party in Discord. We can certainly do that. So let's bid everybody a goodbye, and thank you for coming. I know, Cameron, especially thank you for coming. I mean, I know it's sometime tomorrow for you. I don't know what time, but for those of you who are not here in person and are watching this as a replay, and you have any questions, hop over to Discord. You can send me a private message and I'll be happy to help you with whatever questions you have, walk you through whatever it is that you may need help with. And I think we'll call it a night and we'll do a brief after party over on Discord. Thank you everybody for coming. Have a great night.
Thanks, everyone.